Hello friends, in this video let us discuss about the equivalent circuit of a three-phase induction motor. So we all know that induction motor is a well-known device which works on the principle of a transformer. As the energy is transferred from the stator to the rotor entirely by induction, you can say your induction motor as essentially a transformer, and during the standstill position of the induction motor, that is when your slip will be equal to 1, you can say your induction motor actually a static transformer with the secondary side short circuited. And when you consider the motor is operating at slip, it can be said your induction motor as a rotating electrical transformer with the secondary side short circuited. And we all know that the induction motor must run below the synchronous speed or full load speed. It must run below the synchronous speed or full load speed, because we know that there should be some relative difference should be maintained between the synchronous speed as well as the rotor speed. Now, if we define the slip can be defined as the ratio of the difference of synchronous speed and rotor speed to the synchronous speed. Now, when there is no relative difference, that means I am saying the rotor speed is equal to the synchronous speed, and when it is considered your slip will be equal to 0, and for a short instance the torque will fall. The torque will fall, or you can say it will come to 0 gradually. So as the torque will fall, again your NR starts decreasing, that is it goes below NS, and again as the relative different speed is developed, there will be electromagnetic induction. So once we brief the working principle of your induction motor, if I say this is your stator and this is your rotor, so on supplying a balanced three-phase supply, that means the currents are equally displaced in time domain. When a rotating magnetic field is formed, if the windings of the stator are distributed. Now, the windings are spatially distributed, and on supplying the balanced three-phase supply, a rotating electromagnetic, that is a rotating stator magnetic field is seen, and these rotating magnetic flux will sweep over your stationary conductors, and when they sweep over the rotor stationary conductors, there will be an induced EMF according to the Faraday's law of electromagnetic induction, and as the rotor is a short circuited one, there will be the current flowing in that rotor circuit, and due to that rotor circuit there will be a rotor flux which is rotating at your speed NR, and the stator magnetic field is rotating at speed NS. Now, unless there is some difference between the rotor rotating field and stator rotating field, there won't be any cutting of the stator magnetic field with the stationary rotor conductors. When they are rotating at the same speed, if I say this is my NS and this is my NR, when they are running at the same speed on the same plane, there won't be any relative motion between them, and according to Faraday's law of electromagnetic induction, either of the two quantities, that is a conductor should be moved or either a magnetic field should be moved. So either of them, one should be moved, and it is immaterial whether you are moving a conductor in a stationary magnetic field, or you are moving, or you are changing the magnetic field to a stationary conductor, whatever may be the circumstance, and induced EMF is C. Now, the frequency at this induction takes place, if I say F1 is the supply frequency, that is equal to F is the stator frequency, that is equal to supply frequency F, and your rotor frequency F2 will be equal to, when the motor is operating at slip S, then it will be equal to S into F1. Now, as the rotor frequency is slip times the supply frequency, the frequency of the rotor induced voltage will be, or if I say the frequency of the rotor induced voltage and the frequency of the rotor induced current will get affected by the slip, and if I say E2 is the induced voltage and I2 is the induced current, and considering this slip, they will be S into I2, and this current will be, this is S into E2, and this current will be I2. And similarly, if I say about the reactance, that is X2, this is equal to 2 pi F 2L, and this will get affected by this frequency, and therefore it becomes S into X2. It becomes S into X2 as it is getting affected by the slip. So similarly, here as we are considering the induction motor to a transformer, this is basically how your exact equivalent circuit for an induction motor looks like. So basically there are two types of equivalent circuit in case of a three-phase induction motor, and if anyone asks you what is the purpose of a equivalent circuit, so basically the equivalent circuit for any machine evaluates the performance characteristics as well as it shows various parameters. Like if I say the parameters, it shows the various parameters like losses, which includes the ohmic losses, the core losses, the friction and windage losses, rotor losses, whatever the losses occurring in the machine. So it can be shown by the equivalent circuit by showing the impedances. So we shall discuss that. So you can show the various parameters like losses and the power factor and the efficiency and etc. So in order to evaluate the performance characteristics, basically we are going for the equivalent circuit for any machine, and by knowing the leakage impedances we can calculate the losses, and basically these losses can be modeled by your resistor as well as inductor. These losses can be modeled by resistor and inductor. So the winding resistance is taken into account for considering the copper losses in the resistance, and the winding inductance is taken into account for considering the voltage drops due to inductive reactance. So, and for this purpose only we are taking the equivalent circuit for any electrical machine. For any machine you can say what is the purpose of the equivalent circuit. They are basically used to evaluate the performance characteristics like the losses, the power factor, the efficiency and the voltage regulation and the voltage drops, and many more parameters can be calculated by modeling them to a equivalent circuit. So as we have discussed, there are basically two types of equivalent circuit. So one is the exact equivalent circuit and the other one is the approximate equivalent circuit. Approximate equivalent circuit. So here, as I said, the rotor frequency is S times the stator frequency. When your S is equal to 1, that is at standstill, the frequency of the rotor will be equal to the frequency of the stator. And if I indicate the parameters, if I say this is my supply voltage V1 and I1 is the current flowing here, this is my R1, that is the stator winding resistance per phase, this is X1, stator winding reactance per phase, this is RC, that is the core loss component or energy component you can say, and this is XM, this is the magnetizing component, and let me say this is I1 current, and here I0 is the no load current, and this is your I1 dash, and here you can see E1 is the induced EMF in the stator. These are all per phase values, and here this is the I2 current, and this is your X2, that is the rotor reactance per phase, and this is your R2, and here is your E2, that is the stator, that is the rotor induced EMF. Now by considering the slip S, then it will be equal to S into E2, this is S into X2, and there won't be any effect of slip on the resistance. And what I do here is to make your F2 is equal to F1. From here we have divided it with S. Similarly, if I divide it with S, here also S upon S, this S will get cancelled, and I will be having here R2 upon S. So this will be simply my E2 and this will be simply my x2. Just by making the frequency of rotor equal to frequency of stator. So here your R2 by S, the power is dissipated in this resistor R2 upon S includes the output mechanical power and copper losses. It includes the mechanical power and the output mechanical power and the copper losses. And in the transformer, we have seen that the secondary circuit or the secondary winding is connected to an electrical load. But here, your R2 upon S, R2 is having the power included as output mechanical power as well as the copper losses. Now, since the load is mechanical in the induction motor, we can replace this resistor R2 upon S, your R2, if I say it is R2 dash, it can be replaced by R2 into 1 minus S upon S. So, this is simply what is R2 upon S minus R2. This is R2 upon S minus R2. That means we are subtracting this R2 from R2 upon S. So if I subtract R2 from R2 upon S, as I am subtracting one R2, that means I have to introduce a R2 here. I have to introduce a R2 here. As I am to compensate this subtraction of R2, I am introducing a plus R2 here. So now I can write the mechanical load of R2 upon S to an equivalent electrical equivalent load as R2 upon S minus R2. And by considering the frequency of the stator equal to frequency of the rotor, I can refer my secondary side to the primary side. That is basically the stator of the induction motor is resembling the primary of a transformer and the rotor is resembling as a secondary of the transformer. That means I can refer the secondary to primary side, and that means I can write here this R2 as R2 dash, this X2 as X2 dash, that is referred to the primary side, that is a rotor winding resistance referred to primary side, rotor winding reactance referred to primary side, and this will be your R2 into 1 minus S upon S. So this is how you refer to the primary side, and if I write the parameters here, this is my R1, this is X1, this is RC, and this is Xn. Here the voltage is V1, the current I1, and this is the current I2, and here is the no load current I0. So this is basically how the circuit looks like when the secondary side is referred to the primary side. Now, if we talk about the next model, that is the approximate model. So the approximate model is used just to simplify our calculations, and during no load, so when there is no load connected to the shaft, what you can do is, at no load, the stator impedance drop can be neglected and this shunt branch can be shifted towards the primary. So at no load, what I do is, I will shift this shunt branch here. That means this will be my new approximate model. By shifting this shunt branch to the primary side, as we have considered a condition that is at no load, the drop across the stator impedance can be neglected, and this approximate model is just to simplify our calculations, but this approximate model is not appropriate because of some reasons. So the reasons, what are the reasons for not considering this approximate model? So the first reason you can say, the magnetic circuit of an induction motor has an air gap. So it has an air gap, unlike the continuous core in your transformer, and as you are having a low reluctance path for the mutual flux, The no load current in the transformer is around 2 to 5%, but as we are having an air gap from the stator to rotor, therefore we need large exciting current to produce the required mutual flux. So your no load current here is around 30 to 50%. So this is one reason why you cannot consider this approximate equivalent model. And the second reason is the rotor and the stator inductance are having a large value. So their rotor inductance and the stator inductance are larger. And the third reason is the windings are distributed unlike in your transformer. So because of these three reasons, we do not consider the approximate model, but we consider the equivalent, exact equivalent model only. So that is just the difference comes in the shunt branch only in the exact equivalent model and the approximate equivalent model. So because if you consider the approximate equivalent model, as we have said, the air gap, that is the no load current, is around 30 to 50%. That means these stator impedance drops cannot be neglected at no load, as the current is having a large value compared when you compare it to the induction, that is a transformer, the current is only around 2 to 5%. Then it can be suited for your transformer, but it cannot suit for your induction motor because of these three reasons. Now, if I discuss the power relation by taking this equivalent circuit, so basically, if I say I am having initially a motor input, that is a motor input, that is a three-phase supply, and from the motor input, I am having the stator copper losses as well as stator iron losses. So the power can be used for overcoming these losses as well as it can be supplied to the rotor, that is a rotor input. Now again here, your rotor input can be used for overcoming the rotor copper losses, and the other section can be used for the mechanical output power. And this mechanical output power again can be used to overcome the frictional and windage losses, and again this power will be your shaft power or useful power. So basically the power dissipated in this resistance is nothing but the shaft power or useful power, unlike R2 upon S, which is compromising the output mechanical power as well as the core losses. So this is your R2 upon S, which is compromising the mechanical output power and the rotor copper losses. So as this is having a mechanical load, we are converting it to an electrical equivalent of R2 dash into 1 minus S upon S. Now, as I have considered a 1:1 transformation ratio, then it looks like. Now, if I consider some ratio, let us say K, that is equal to number of turns per phase in rotor to the stator. So then your equivalent circuit parameters will be coming as R2 upon, this is K square, this is K square, and this upon K square. Your current will be I2 into K and the EMF E2 upon K. By considering the transformation ratio N2 upon N1, now if you consider it as 1:1, then it will be simply R2 dash, X2 dash, and this is E2, and this is R2 dash into 1 minus S upon S. So now here your rotor input or the power generated is basically the power dissipated in the resistance R2 upon S, that is 3I2 into 3I2 square into R2 upon S. This is the power generated for the rotor input. Now here the power dissipated in this resistance is nothing but your rotor copper losses. So if I say this is my P generated, your rotor copper losses will be equal to 3 into the current is flowing I2 here, 3 into I2 square into R2. So that means I can say this is nothing but S into PG. If I multiply here S will get cancelled, that is nothing but 3 into I2 square into R2, that is nothing but S into your PG, and your mechanical output power can be Consider by subtracting PG minus SPG. So if I subtract the rotor copper losses from the rotor input, I will get the output mechanical power. So this is your output mechanical power, and from this output mechanical power, if I subtract the friction losses as well as the windage losses, I will get the shaft power over the useful power. So this is all about the equivalent circuit for an induction motor. I hope you understood well. Please subscribe to the channel. Thank you.